Where's the
I think so.
microphone? Oh, right there.
Just give it a second.
Yeah, nice to meet you. How's it going?
Okay, good morning, everyone. Hello. Welcome to day number 3. So today we're going to have a day of quantum chemistry by our senior research scientist, Nathan Fitzpatrick.
Yeah.
He's coming from the UK. He's a Quantinuum. And just to let you know, so pretty much today's morning schedule, like our lectures with 10-minute breaks. Then we're going to have lunch here at 1:30. We have to take the shuttle or walk down to the lab again at the Diagrammatic guest house. So at 2 p.m. we're going to have quantum chemistry labs today. So make sure everything is charged, charging points down in the lab. But without any further delay, let's start our day on quantum chemistry. Thank you.
Hello. I guess everyone hear me, I guess. Sounds good. So I'm going to speak about quantum computational chemistry. I hope you're looking forward to 4 hours of me lecturing today. I am looking forward to it. So the idea is essentially to start from ground zero, basically. So I imagine some of you are from a computer science background and haven't even done quantum chemistry before. And then hopefully, even for the physicists, this might be some new stuff. And hopefully, try and give you some of the intuition behind quantum chemistry calculation, which I think kind of is quite mysterious to a lot of physicists. So why study chemistry? So at the basic level, it is why do atoms stick together, which is known as the study of chemical reactions. So the study of chemical reactions essentially is the analysis of bond breaking and bond forming reactions. So you may have seen these curly arrow drawings around, maybe giving you nightmares from your undergraduate, perhaps. So these are extremely qualitative, and it's kind of amazing that these work to describe chemical reactions so well. But you'll see some of just the simple analysis working from atomic orbitals gives you this picture, and it leads to a huge amount of chemical and biological complexity. So particularly if you just think about the atomic orbitals, how they interact and the electron density, you can actually build up quite a good picture of chemical bonding. But if we want to go a bit deeper, why study chemistry on computers? So we have, essentially, it's energy as a function of nuclear geometry. Okay, and we have this thing called the potential energy surface, where each point on this surface is a quantum chemistry calculation. It can be semi-empirical. The level of theory is up to you. It's your choice. Obviously, you'll get better results if you use a more advanced level of theory. And you can see at the minimum, so these point A and C, these are what we call equilibrium geometries. This is where the molecule is stable. It likes to sit in these things, and these are the kind of the relaxed geometries. But obviously, to form a bond, we've got to go from A to C. We need to go via B. B is known as a transition state. And it's where the bond breaking happens. So you can see, if we go along this reaction coordinate, where the reaction coordinate is this hydrogen. Is this hydrogen, this white thing being passed between the two oxygens. You can see it doesn't like being in the middle, so there's a high energy here. But obviously, to get from A to C via B, we need to increase the energy of the system. Okay, so this is particularly important for biological processes and studying these accurately, because if you look here, we have, for example, this is the oxidation of glucose. This is important for us to be alive. And without an enzyme, it requires a lot more energy to kind of go from this equilibrium geometry of glucose to carbon dioxide and water. So, so ideally, we want to be able to understand why enzymes can reduce the energy barrier. But obviously, the problem is that enzymes, these biological systems, are huge, loads of degrees of freedom. Therefore, we can't really study all the quantum interactions. So this is one of the motivations of quantum computing, is it allows us to break the scaling problem because we can go for 2 to the n number of degrees of freedom. So typically, our best results at the moment are kind of quite inaccurate for these strongly correlated systems. And the really famous one is FOMOCO in the nitrogenase. So FOMOCO is the reactive center in the nitrogenase enzyme, which is found in the soil. It uses sunlight to convert nitrogen and hydrogen to ammonia, which is important for fertilizers. But we have to do it with the Haber process, which uses 2% of the world's energy on a day-to-day basis. So if we could solve this, and if we can figure out why the reaction barrier is so low for FOMOCO, we can obviously save a huge amount of energy. And this is kind of the poster child, this FOMOCO versus Haber process, is why we need quantum computing. Okay, so briefly I'll just talk about, so if the potentiality surface is this kind of, when you go into high dimensions, so I showed you previously a 2-dimensional one. Here we have kind of, this is a 3-dimensional one, and it actually generalizes to 3n minus 6, because for every atom, you have 3 dimensions, with x, y, z, but then obviously you have translational, global translational and rotational, which remove 6 degrees of freedom from the problem. So obviously, so the minimum are those reactions and products and these saddle points of transition states. And you can do this in numerically, formally, with kind of Hessian analysis, where the Hessian is the 2-dimensional matrix of the second-order derivatives. And then, interestingly, the molecular properties come from the slopes and the curvature of the potentiality surface. For example, if you've got a very steep well, it's going to want to fall down to that equilibrium geometry very quickly. So there's the reaction, the force required for that reaction to happen is more. But for the purpose of this talk, we're not going to worry about potentiality surfaces. So moving on potentiality surface is what causes chemistry. But in order to get a good potentiality surface, we need to calculate the single energy point for a given geometry. And then for the rest of the talk, we're just going to be focusing on one grid point, because if you use kind of the cheap methods like DFT or semi-empirical, you'll get a potentiality surface, but it might not be the right one. So we need to get accurate potentiality surfaces, and to do that, we need to use very high-order methods like quantum computing or exact diagrammatization, if you're familiar with that. Okay, so some of you, I'm going to start kind of what you may have seen before. So just kind of want to introduce the quantum chemistry Hamiltonian. So the quantum chemistry Hamiltonian is the fully interacting fermion problem, where we have this, essentially we have these one-body interactions and these two-body interactions. And then we have these fermionic creation annihilation operators, which I'll introduce later. But essentially, if you kind of squint, you can kind of see that it's like the Fermi-Hubbard model, where rather than having nearest neighbor interactions, we have all possible global interactions. Okay, and then rather than having just these parameterized weightings for these interactions, these G and H, these are actually these spatially dependent objects which contain a huge amount of information, and they're responsible. There's many, many years of development just find these parameters. So these parameters contain all the information of, so this shape here, this orbital, this is just one of these indexes here. So to get all the information for PJ, PQ, RS, each individual indices, contains like the shape and the geometry of these molecular orbitals. So I'm going to be speaking quite a lot, maybe the first lecture and a half, about basically just obtaining these molecular orbitals. Because if you start with you can just start here in quantum computing if you want to be naive. You can just say, you may have used PySCF or some other driver But that gives you your quantum chemistry Hamiltonian, which you then give to a VQE or phase estimation or whatever. But it's like, to actually get these weightings is a huge amount of work, and to actually understand the chemistry, you need to understand how you get the weightings of the interactions. Okay, so we're going to speak about orbitals, basis sets, integral evaluation, and most importantly, Hartree-Fock theory. Okay, so I'm going to start from the total basics. There may be people who haven't studied quantum mechanics at a high level here. Like, obviously, there's lots of people who do theoretical computer science in this field. So, essentially, we're only going to be worried about the time-independent Schrodinger equation because the quantum chemistry Hamiltonian is just dependent on. There's no time-dependent terms, so we can just use this time-independent Schrodinger equation. And essentially, the time-independent Schrodinger equation will always have this form. You'll have a kinetic energy term, and you'll have a potential term. And in 3 dimensions, the potential energy term is related to del squared. Sorry, the kinetic energy term is del squared. And this will always be the same. But the behavior of the system is encoded in the potential of the Schrodinger equation. So depending on what application you have, you'll have a different V, and that will determine the overall wave function, because this is a differential equation. So you can use, for a lot of the toy systems, you can use differential equation methods to solve for psi. And if you have different boundary conditions or terms in your Hamiltonian, you will end up with a different solution to the differential equation. Okay. But the moral of the story is the Schrodinger equation really depends on the potential and the boundary conditions. So you may have seen it like this. This is kind of what we call a Hamiltonian eigenvalue, the Hamiltonian eigenvalue equation, where we group the operator terms. So I should say this is Planck's constant h bar, and this is the mass of your particle. So we're just talking about a single electron here. I apologize. Yeah. Single particle. And then we can group all these terms. We kind of put them as this H operator here. And then that will generate this kind of, it will generate the same wave function, psi, and then this energy term, this energy weighting here. Okay, so this is what we're trying to solve to get the wave function, given a potential and some boundary conditions. Okay, so Schrodinger, when he came up with his wave equation, which I think was in 1927, I think, he then released, 6 different papers solving the time-independent Schrodinger equation using lots of very powerful differential equation methods, which had come from kind of Laplace and people like that, looking at planetary motion and things like that. So even though these equations look extremely scary, there's a lot of kind of, the theory was quite well known by this point. So the ubiquitous one, which you probably all solved in your first year or second year physics course, is the particle in the box. And it's the simplest example of how potential, 1D particle in the box, simplest example how potential and boundary conditions can govern the wave function. And there's some slightly more difficult ones, such as like the free particle in 3 dimensions. This introduces separation of variables and the idea of product wave functions. And then there's also the stationary hydrogen atom. So this is the one that we're really going to focus on today. So I don't have time to really, so some of the exercises will be to solve these if you haven't before. But what we're really going to focus on today is the solutions of the hydrogen atom, because that's where all chemistry can be built up from. Okay, so the first kind of analytical solution of the Schrodinger equation is this quite simple model, where you essentially have this 1D dimension, and then you have these infinite potentials, and then you have 0 potential between 0 and L. Okay, so you can see the kinetic energy is kind of represented by this cool drawing that I made. So the Schrodinger equation looks like that. So it is a bit confusing because there's no potential in this form of the equation. So we have And this m here is the weight of the electron, or the particle which you choose. But the particle is included in the boundary conditions of the solution. So one of the exercises will be to solve this. But essentially, the moral of the story is, when you solve this equation, you end up with these quantized energy solutions, which are given by this parameter n. So the rest of these are constants, and L obviously as well. But given a fixed length of box and a fixed mass, n is the only thing that can change. So what this represents is essentially you get standing waves between these two potentials. And each standing wave has, like the harmonics, these have different energies. So this is really the first indication that Schrödinger showed that you get quantized energy from his Schrödinger equation. So the stationary hydrogen atom is kind of where quantum chemistry really started, in my opinion. So here we have a single electron represented by M1. Ooh. And we have this kinetic energy operator, del squared. And then we have this V. So this V is this spherical potential. Okay, so it's just this totally symmetric spherical potential. Okay, so you can see this now. So it's just 1 over. So we have, it's 1 over r squared, and then this is the mass of the proton and the mass of the electron up here. Okay. So essentially, so the potential felt by an electron in the sphere will be dependent on a 1 over r term. Now you can try and solve this problem in Cartesian coordinates, but it's not very natural because you have spherical potentials, right? So you can switch the polar coordinates, which looks terrifying, but as I said before, this is all quite well-known theory from planetary motion and things like that. So essentially what you have here is, rather than that x, y, z, you have what are called, you have the radial dependence, which is r, you have the theta, which is the equatorial angle, and then you have the azimuthal, I think that's how you say it. So you basically have rotations around the equator and rotations around the vertical axis. And the Schrödinger equation then, the kinetic energy operator looks like this. And V is just equivalent to 1 over r. Yeah. So what this basically allows you to do, if you notice, you have 3 different terms in your kinetic energy operator. So again, don't try and solve this. This is all textbook stuff, but I'm just trying to give you the main ideas. So you notice you have the r terms here, you have the theta terms here, and you have the phi terms here. Now, what this means is when you have a Hamiltonian like this, or any differential equation where you have non-interacting terms in the linear, because this is linear equation, it basically means that you can solve each one of these you can solve each variable on its own using a technique called separation of variables. And this is actually really important for Hartree-Fock and in single electron wave function later on. But basically what it means is you can solve an independent system of equations, and then you can basically form the total system by having a product of those independent systems, which is a very powerful method. So you can kind of see that here. So if we assume that we have this product wave function, which is dependent, you have a term for r, a term for theta, and a term for phi. We just substituted this into the previous equation. Looks a bit nasty because you've got this extra potential term. But you can do some rearranging, and you get this nice set. You can divide by the wave function, the product wave function, you get this nice equation. And this can be solved by a separation of variables. Now, this takes 5 chapters in most textbooks. So if you are interested in looking into this, I highly recommend the book by Linus Pauling, Introduction to Quantum Mechanics. It was written in 1937, but in my opinion is the best description of how to solve the hydrogen atom. And it really gives you kind of the idea of how these problems are being solved back then before computers. A lot of the modern quantum chemistry textbooks are, you just jump into kind of the numerical solutions, which don't give you as much insight into the problem. Okay, so here's the three equations that you get from separation of variables. You got your phi equation, you got your theta equation, and you got your radial equation. Now these are all, now you can solve these using some quite an intense differential equations methods. But what this happens, so I've jumped a lot of steps here, but more summary, you get this is the solution of that product equation. Okay. And as with the wave functions in the particle in the box solution, which was quantized by some quantum numbers depending on the harmonics, here we have a similar idea where we have quantum numbers dependent on the radius. It's called the principal quantum number. We have the magnetic quantum number, which is around the equator, L, and then we have, so we have the angular momentum quantum number, which is around the equator. We have the magnetic quantum number, which is the azimuthal degree of freedom. So yeah, it's quite scary, but as I said, like a lot of these polynomials, there's loads of work that happened here in the 1800s. And yeah, so, and the main tool they use is the spherical harmonics, because obviously we have spherical symmetry in the potential. This makes everything easier. Okay, so now you may notice that the energy when you solve this, because we have no electrons, extra electrons, the energy is dependent on even though the wave function contains n, l, and m, it's quantum numbers, because we have a non-interacting single electron picture, the solutions of the Schrodinger equation for the hydrogen atom, or the spherically symmetrical particle and spherically symmetric potential, they only contain the principal quantum numbers n here. Okay, so I mean, this is, so it's, if we want to go to larger atoms, larger ion, so like lithium, helium, beryllium, etc. This theory does break down a little bit, because obviously we have you need to take into account the interactions from the inner electrons, which is called screening, if you've heard of that, nuclear screening. So, but it's qualitatively, it still works quite well. So now you can kind of start to do some analysis with these wave functions, looking at the density, where the density is essentially psi squared. So the solution, I've jumped ahead slightly. So if you take that equation that you saw, that really scary equation that I showed you, and then you put in, so this psi here, we have n, l, m. So that's these indexes. So principal quantum number, we have the principal quantum number 1. There's only 1. Then we have principal quantum number 2. We have 2. We have the s orbital here, and then we have, so that's 2, 0, 0, and then we have so anything with principal quantum number 1, so n, 0, 0 is known as an s orbital. Okay, so that's a totally symmetric solution. So you can see here we have psi 1, 0, 0. This is just parameterized by this. You can see here, this is just a radial exponential here. It's an exponential parameterized by the radius. So this is a spherically symmetric 3D thing, or a sphere, basically. And you can see the same applies for the 2s, but now you have kind of this product here, which gives us nodal behavior. So if you see the 2s, rather than being a sphere, is actually this kind of sphere, but with an inner sphere inside it as well. And the inner sphere comes from this product term before. And then when you start to have 2, 1, 0, and 2, 1, 1, anything with L equals 1, that's a p orbital, and that's when you get these dumbbell-like shapes here. Okay, but what I'm trying to show is that the shapes of the orbitals, all of the hydrogen orbitals, all come from the solutions of the spherically symmetric single particle wave function. Okay. So you can do some analysis on these with these things called the radial distribution functions. Now that what the radial distribution function is essentially is use Born's rule, which essentially is you take the density of your wave function solutions, which is just essentially you take one. You basically square the product of them. So here we're looking at the 1s, which is 1, 0, 0. Remember, this is the simplest one, which is just the spherically symmetric ball. It's just exponentially decaying along the radius symmetrically. You can see that we have. You can see that and there's obviously from when it starts decaying when you get away from the nucleus as well. So you can see here that if we analyze this along the radius, you can see that the probability of finding an electron has this distribution function. And then this is the 2s, which is equally symmetric, has this function. But you have this nodal character here. So the principal quantum numbers all have these. As you go up in principal quantum number, you get an extra node in your wave function, which in the s orbital picture is a ball within a ball within a ball. If that makes sense. Okay. But the main point to take is that the hydrogen atom gives you the shape of where the electrons like to sit. The solutions of the hydrogen atom give you the rough, the best approximate of how the electrons like to behave in large molecular systems. So this is really where you need to start to do quantum chemistry. So having a good understanding of these molecular orbital, these atomic orbital shapes, really gives you some intuition in chemistry. This is if you think about a lab chemist, they're always thinking about these shapes and how they can fit together, things like that. So this is really where the chemical intuition comes from. Okay, and this was actually experimentally verified in 2013. You think using Xray diffraction, I think. And you can see that 90 years after Schrodinger derived the equations, only 9 years ago, they actually were able to verify this. So these are excited hydrogen Xray diffraction, I think, which is really cool. So essentially, in the presence of no extra electron, so the single electron picture, the hydrogen atom is essentially correct without, because there's no relativistic effects or anything like that. Okay, so, and what's very, very interesting is that the solutions of the hydrogen atom, they predict the structure of these orbitals. It turns out that the periodic table structure, which was determined before the solutions of the hydrogen atom, is grouped into essentially sp, d, and f orbitals, which are essentially the n, l, m solutions of the Schrodinger equation. So Schrodinger actually essentially verified the structure of the periodic table determined by Mendeleev. So you can see here, we have going down in principal quantum number, we have n1, 2, 3, 4. This block here is called the S block. These are all the spherically symmetric. These are all the outer electrons in the spherically symmetric. So yeah, the periodic table is structured on the valence electrons, which is the outermost electrons, and then the electrons in this block are known as the orbitals in this block. This block in the periodic table is known as the S block because the outer electrons are all in S orbitals. And then this block here is known as the p block. And their outer electrons are all in these p orbitals, which are these dumbbell-like shaped ones. If I go back. Yeah, so the s orbitals are these ones, and these are the p orbitals here. So that's one p orbital. I don't know, who made this figure? So this is one p orbital as a dumbbell. This is another p orbital as a dumbbell. Another p orbital dumbbell. Yeah. Okay. So yeah, and then in the middle you get these what are called the d orbitals, and essentially these are grouped into kind of these. These all the blocks have the same principal, the same outer electrons. So have outer electrons in the same in a spin orbital in an orbital which has the same quantum number solutions of the hydrogen atom, which is very cool. And then you got the lanthanized and the actinized down here, which is the f orbitals. Okay. So and you can kind of see this with. So you kind of what this is showing is this is rather than taking a qualitative approach. This is kind of the quantitative analysis of this. So this is the ionization energy, experimental ionization energy. So what this is showing is the energy it takes to take your most outer electron and remove it. So that's kind of telling you the energy of your orbital, your last filled orbital. And you can see that like it's quite good. Like so you can see here this is H to HE. This is the first principal quantum number, and that just goes up monotonically. And then L to neon. This is the second principal quantum number. And then we have the third principal quantum number. And then things start to get a bit confusing when we have the d orbitals. And then we have the f orbitals. But you can see the blocks do monotonically increase, which is kind of what is expected from the solution to the hydrogen atom. But the problem is when we start to introduce when we start to include the electronic interactions of the inner electrons, then the theory kind of breaks down. But it's still at a quantitative level. But they're roughly qualitatively correct. And it's basically due to as you increase the nuclear potential as you go up the group with the same quantum number. Because obviously, as you go along the group, you're adding more protons to the nucleus. So the attraction of electrons to the protons increases, so it requires more energy to ionize them. But obviously, this whole approximation that we've spoken about so far neglects electronic interactions. And of course, the relativistic effects for the lanthanides. So like, for example, gold would not be gold if we didn't include the relativistic interactions, because the core orbitals travel at near the speed of light. Yeah. Okay. So this is kind of what is really seen. You might have seen this in your chemistry classes at A level. So if the solutions that we just derived before, these would have, for all the things with 2, these would be the same level. And then all the things with 3 would be the same level. But obviously, what happens is that because the p orbitals are in these dumbbell shapes and they're more diffuse, when you start to include the core electrons, the p orbitals. And yeah, this is slightly confusing. So ionization is up here. So this is more energy to ionize here. So yeah, so this is larger energy gap. So obviously the p orbitals are less strongly bound to the nucleus because they interact less strongly with the inner electrons. And this is what is called shielding. So the p orbitals are shielded less, or sorry, shielded more. Wait, yes. So the p orbitals feel the effects of are repelled by the nucleus. Sorry, they're repelled by the inner electrons more. And that's why the ionization energy is lower. But, so to solve this, we need to include these electronic interactions. Okay. And this is where Hartree-Fock theory and all the motivation for Hartree-Fock comes in. So obviously in molecular energies, we have all of these. There's lots of terms in the Hamiltonian which are neglected. So you have vibrational, rotational, and nuclear spins. These all decrease in value. And we essentially neglect, and there's translational as well. We basically neglect all of these and just focus on the electronic energy. Okay, so now we're starting to think about molecules. Okay. So now we have these are all the terms from the molecular electronic Hamiltonian, just for the electronic energy. So we have here so I hope you like my drawing. It's color coded. So we have the kinetic energy operator of the electrons. So we're assuming I must say we're using the Born-Oppenheim approximation here. So we're assuming that the nuclei are fixed in position, and then the electrons are just whizzing around these fixed nuclear positions. And so you can see the kinetic energy is represented by the yellow, and then we have the nuclear electron interaction is represented by green. You can see this is a Coulombic term, which is 1 over r. Oh, should that be squared? Yes. That should be squared, I apologize. So you can see here we have, this is the mass of the electron times by the electronic mass times the number of protons in the nucleus, which is Z. And then, obviously, RIA is the distance between is the distance between distance between the nuclei and the electron. And then we have this red term, which is this kind of instant. This is a two-body electronic interaction term. And because these are moving electrons, this is not. You can't solve this term like very easily. There's actually not. It's a three-body problem. So it becomes very difficult. And then you have this fourth term, which is the nuclear interactions, but we tend to remove that because the nuclei are fixed, so they're not going to change over that. So you can actually just calculate that and add it in at the end. So the problem that we're trying to solve with electronic Hamiltonian is actually this one. This should be squared. I apologize. These R's here. This is Coulomb interaction. Sorry. So the charge interaction. So now we have these three terms in the electronic Hamiltonian, molecular electronic Hamiltonian. We have you have the Coulombic interaction of the positive nucleus and the negative electron. We have the kinetic energy of the moving electrons, and then we have the electronic interactions. So these are what is really difficult to solve. And actually, most of modern quantum chemistry is actually trying to solve this term rather than this term. So it turns out, if you notice, the nuclei because the nuclei are fixed in position, they're not variable. So it turns out that we have a single electron term here and a single electron term here. And what that means is we basically have a non-interacting set of terms in the first part of the equation. Okay, so this can be solved with this product type approach, where you have when you have a separable differential equation, you could obviously use separation of variables and solve the individual term each time. So, And then this term's not separable, obviously, because you have these electron-electron cross terms. And it's essentially because the instantaneous positions are affected by each other. So this is incredibly, yeah, so what we do is we just get rid of it as an initial qualitative approximation. So, and then this is called the linear combination of atomic orbitals Hamiltonian. Okay. And we literally just have the kinetic energy of the electron and then the kind of the electronic interaction. We have the Coulombic interaction with the electron and the nuclei. So you can see the sums in this simple picture. Yeah, so you have these 4 sums here, which is represented by the arrows. And then we have 2 terms for kinetic energy. Okay. All right, so now we've got the separable differential equation, or separable linear operator. So it means that we can use separation of variables and we can solve the global molecular picture with a single electronic product wave function. Okay. But so the way we go about this is the first idea to try and solve this molecular problem with this very simplified Hamiltonian that we've picked. Is we use the solutions of the hydrogen-like atom. So these shapes, these orbital shapes, we use those as a basis for this Hamiltonian. Okay. So and I must say, so there's something called the Pauli exclusion principle, which essentially means that the solutions of the Schrödinger, the hydrogen atom that I showed you before, they have space for 2 electrons. And that's because you can basically have no repeating quantum number, but there is a quantum number that I ignored, which is called spin. Spin's a fundamental property of the universe. It was discovered by Jordan, and it has this SU2 symmetry. But what we basically have here is we have what is called a spin orbital. So this is really important. You might have heard this. You might have heard this from. You might have heard this like from your lecturer or something like that. So what spin orbital is essentially you have this psi here. The psi is the spatial orbital wave function. The spatial orbital is that hydrogen atom thing, the shape, but then that's got space with 2 electrons. And then the individual electronic wave function is called the spin orbital. And it has 2 variables. We have r, which is the distance, and then we have sigma, which is a discrete spin variable, and it typically represents spin half or minus spin half. And we often group them together into this thing called the position spin variable, called x. Okay, so that's what it means. Okay. Couple of minutes. So we then, so we take the Hamiltonian and then we solve it in this single electron picture, and that's the single spin orbital picture. Okay. So we take one term from that basically one of those Hamiltonians for each electron, and then that's totally valid to then just solve it for each one, and then form a total molecular wave function and add them together. And then we use the linear combination of atomic orbitals, as you can tell by the name. We form a molecular orbital from a linear combination of atomic orbitals. Okay. So you can see here that we have a sum over atomic orbitals, weighted, which is these spin orbital-like things that I just showed you before. And then we have this linear weighting on for each spin orbital. It's a bad quantitative picture, but this is actually an adequate way of getting kind of qualitative results in the lab. motivator called the arrow pushing that you see before. So let's consider the simplest molecular system now. Okay, so we're doing chemistry finally. So we've got two hydrogens interacting, and then we say we've got these. We take the simplest single electron solution, and due to symmetry arguments, you can just isolate all the s orbitals. Don't ask me about that, but it's to do with group theory if you're interested. Well, please do ask me about that, actually. That's my favorite topic. But so basically, you can isolate the s orbitals due to symmetry arguments, and then you can solve this you can solve the interaction. So you basically say the two s orbitals on each hydrogen. You say you let them interact, and these are spin orbitals, so these are single electron. So you have the spatial orbital, which is the s orbital, with only one spin occupation on each side. And you solve it. Now I've introduced basis. When we apply this basis to the Hamiltonian that we showed, you get what's called the secular equation. Now I don't have time to derive this in this equation, in this lecture, but essentially, when you have a Hamiltonian, you introduce a basis, you will always form a convex optimization problem. And that's due to what's known as the Rayleigh-Ritz variational principle. And there's an exercise in the things to solve this. But what that gives you, basically, is that whenever you solve this, you get from the Rayleigh-Ritz variational principle, you solve it for a minimum, this equation drops out. And what this equation shows is that the solution of this eigenvalue equation will always be the global minimum for this basis, which is extremely powerful. So you see this in all of quantum chemistry and all of kind of exact diagonalization methods, things like that. And this is kind of really fundamental. So it's that the secular equation and the variational principle are two of the founding principles of quantum chemistry. Okay, so what does this look like from a mathematical setting? So we have the, so we saw we had, sorry, I should go back. So this H here is called the Hamiltonian matrix. And now we've got this non-orthogonal basis. Now, obviously, the atomic orbitals are orthogonal in space, but bear in mind, we're not in this. They're not on the same. They're not in the same point in space, so they're not actually orthogonal wave functions. And then you have this overlap matrix, which accounts for orthogonality. So this is a generalized eigenvalue problem now. So what do these elements look like? So a lot of quantum chemistry really comes down to solving these Hamiltonian elements. Now this is one of the, because we're working in that kind of a first quantization picture here, you notice their functions of distance, the wave functions, which is not actually the case in now second quantization, but it gives you an idea of how you build up these elements. So there's a whole field of first quantization in quantum computing, but basically what you see here is you have the wave function on each side. So you've got this, you see you've got your wave function, you got your operator, and you got your wave function on the right side, integrated over all of space. Now the operator, you can see here, this is if we just take the s orbitals, we showed that these come from the radial solutions, radially symmetric solutions of the Schrodinger equation on both sides, and then they're kind of sandwiched by this. You have this operator which is sandwiched by both of them, and you can see the operator now has, we've got the kinetic energy term. Remember we're in a single electron picture here, so we have the kinetic energy of one electron, and then we have the kinetic energy of one electron interacting with the nuclei on the first hydrogen and the second hydrogen. Okay, so this is a pretty nasty equation, but you can actually solve this with kind of scipy dot integrate or something like that. I think it would be really cool to actually write, if someone wanted to write the solver for this, for the s orbitals. So just, you can see that you can just plug this in. These are all functions that you can integrate. You just need to discretize some numeric grid over the radius, the radial function. And then we have the overlap matrix. And I think the overlap matrix have kind of a intuitive picture, because it's literally in this first quantizational picture where you have where the wave functions are distance dependent. You get, that's probably the wrong. The wave function is always distance dependent, but in first quantization, the distance dependence lives on the wave function rather than the operator, like in second quantization. But anyway, you get this kind of physical overlap picture where you have these kind of exponentially decaying functions when the nuclear cusps. And you can see that the overlap will increase with how much they physically overlap. Okay, so I'll just quickly, I'll do a few more slides and then I'll stop. So I should work this out. Okay, so this is kind of what you can use this. So if you notice that equation was an eigenvalue equation, so it turns, and then we had two basis functions. So that means there'll be two solutions of the s orbitals in hydrogen. We have, we solve for the one electron picture, and then we fill it up with two electrons, because we get one solution for one electron and one solution for the other electron, but they're the same due to the spatial orbitals being the same. But basically you have two interacting hydrogen atoms, and then you get what's called a bonding orbital, bonding molecular orbital. This is super important now. And then you have an anti-bonding molecular orbital. So we take the two spin orbitals, and then we form a molecular orbital. Now, it's quite confusing because you get two molecular orbitals down here, one for the spin up and one for the spin down, and two molecular orbitals up here for this, but these are vacant. But what we call the sigma G, this is the bonding orbital, and this is kind of a positive linear combination of the two s orbitals. And then we get the sigma U star, stands for gerade and ungerade, I think, which is German for spherically symmetric. Symmetric across the center inversion, I think, and anti-symmetric. And you get this negative combination here. So this is really kind of what you get this bonding and anti-bonding picture. And it's not normally this simple when you have lots more spin orbitals, but in the kind of the two spin orbital system, it's quite nice to see that you get bonding and anti-bonding. So what this is showing, just to summarize, you're joining up these two, and then you form these two here. Okay. And then you can kind of look at the Born rule now, the densities for this new molecular orbital picture. Okay. So if we look at the bonding orbital here, so you can multiply this out into the two spin s orbitals if you wanted to. But what you see is the Born rule, you get these kind of, this peaky, the two s orbitals are really these peaked nuclear cusps. And then you get the bonding interaction here, which is like this favorable density in the center of the bonding orbital, and that's why you get this joined electron cloud. And these are all just mathematical solutions. And then you have the antibonding, which is obviously you have a positive and negative interaction here of the same function. And then that's where you get this nasty function here of the wave function. But obviously, when you take the Born rule, you're squaring it. So then you get this unfavorable area in the center where the electrons are like, ooh, get away from me. So that's why you get this. That's why you see this anti-bonding, and that's why you have the positive and the negative colors here. So these are called the phasors. Okay. I'll just go. Yeah. So the summary is you can build up a very simple molecular bonding picture with the hydrogen-like atomic orbital. So you get the simplest idea, you don't even have to think about the mass, really. It basically boils down to, if they have the same shape and they're overlapping of the same color, there will be a favorable interaction. So this is where the chemists get so much of that chemical intuition from, is that they're kind of implicitly solving the linear combination of atomic orbitals in their head by kind of like overlaps with like favorably. And that's why you get this bonding picture. So here you have the two s orbitals bonding to form favorably interacting to form this sigma bond. We call the sigma bond because it's totally spherically symmetric, circularly symmetric around the bonding axis. And then when you have two favorably interacting p orbitals, you get this kind of delocalized. You get the positive phase delocalizing at the top favorably, and the positive phase delocalizing favorably at the bottom. So you get like this two sausages almost above and below the bonding axis. And this has kind of 180-degree symmetry. Okay. And this all comes from, if you're interested in group theory, these labels all come from point group symmetry for the irreducible representations of the finite groups. And then, yeah, so you can see now if you start wanting to go to, you can obviously add all the there's an infinite number of solutions for the hydrogen atom, right? So you can start to form all these bonding pictures for two hydrogen atoms. So you can kind of see, it's quite intuitive. You just have favorable interaction, non-favorable, favorable, non-favorable for the same shape. Then the p orbitals, they're all the same, but they're on different axes, so they can actually spatially interact slightly differently. So you get sigma bonding p's here, pi bonding p's, anti-bonding pi p's, and sigma anti-bonding sigma p bonds, sigma p orbitals. And you can kind of see the p orbitals interact less strongly than this. So the pi bonds are less strong than the sigma bonds because they have less physical overlap. And that actually comes from the overlap term in the Schroeder equation having less magnitude for these two combinations. So yeah, so this is the chemical intuition that people sort of have. And it's basically just orbital overlap. That's all you think about. So benzene is these 6 carbon atoms. You know, carbon is in the P block. It's got these PZs, we call them. So you have PX, PY, and PZ. Now all the PZs from the carbons, you have 6 of them. So this would be a 6-dimensional basis, right? 1 PZ for each carbon atom. And then you get these favorable interactions here. And this is the pi bonding interactions of benzene. So you get this delocalized cloud. And then you can this is really cool, because if you start to think about like graphene, you can see why you have all this delocalization property of graphene, because the electron clouds are all it's basically extrapolation of this to like tessellations of these carbons. Okay, I'm going to stop there for now. Any questions? Let me know.
Okay, do we have a quick question or, yeah, okay.
All right, maybe it's a bit early, but I need help building my chemical intuition. So if we look at the diagrams of the atomic orbitals,
yeah,
right, where you have light and dark
yeah,
patches, if I want to make them fit together, should I be trying to put light on top of light or light on top of dark?
You want them to overlap with the same colors. So if I get back, I mean, you can kind of see it here actually. So if you look at this, this is a very strong. So we have this is the most strongly bonding, because we have vertically we have 6 of the same color interacting, and then you have the negative phase, 6 of the same color interacting on the bottom. Then you can see them. Now the energy of the bond is less strong here, because you start to have, there's more mix. You see up here you've got one negative, 2 positive, 2 negative, etc. And then you can see up here is the most weakly bonding. This is the strongest anti-bonding. This is because you have totally out of phase things. So if you have more things of the different colors touching, that's bad, basically. Yeah.
And then, so I noticed when you were doing the ionization energies of various elements,
Yeah.
indium and gallium have really low ionization energies. Does this have something to do with why they're used in 3-5 semiconductors?
I am not an expert in this matter, but So I believe that's to do with the fact that they form 2D materials like graphene, gallium arsenic. I think that's why, because it's a fabrication, it's easy.
Okay.
But gallium is there. I mean, so let's go to the periodic. I don't have the periodic table in my head. It's been a long time since I've actually done chemistry properly. So where's gallium? Someone help me.
To the right, one column, and there it is.
Okay, so it's the first p orbital. So you've changed your quantum number, and then the p orbitals, it's the first one. So that's why it's at the bottom. Yeah, it's why it's lower. I'm not
Okay,
sure.
so one electron has just been pushed up into an orbital, and it's easy to peel that electron off.
Yes, exactly.
Okay.
Yeah.
Okay, one quick question.
You can see here, actually, Ben. You can see that it's the first p block, because you can see the start of the p block ionization. So the 6 p orbitals you got. So gallium's the first one, and you got the rest that's a crypton. Yeah. And then when you have more nuclei, you've got obviously stronger potential interaction. So it's like the nuclei holds onto the electrons much more. Yeah. Okay. Sorry.
Thank you for the wonderful lecture. I'm here. Okay. So in the linear combination of atomic orbitals, there was a section equation, right?
Yeah.
Yeah. So you have 4 parameters for variable c, right? Can you just add up all possible linear atomic orbitals and make a linear combination of them? And I don't know, by brute force or machine learning, just like go up to as much as you can and learn everything.
You could just have all of them if you wanted to,
Yeah,
and then solve it.
And would there be any significance to it, or that what's the
will-
implications?
You'll see the symmetry. If you just were naively to throw all the spatial orbitals, you will see, and if you're to machine learn it, you will see them group into symmetry objects. So you'll see this Hamiltonian will get blocked into symmetry groups, so irreducible representations. Yeah, so imagine the machine learning, if you were to throw all of them at, all the orbitals at it, it will just find the physical symmetries present in your problem. And that will be represented by the blocks of this Hamiltonian, which will then result in you'll have eigenvectors which have a lot of zeros, which don't allow for interactions and other things.
Okay, good. So let's have a very quick break. Thank our speaker for the first hour. And we'll be back soon, okay? Stop 5 minutes before.
Yeah.
Time, so that we have 5 minutes.
Is that a request? Sorry about that. Was that because it...
Okay, shall we start? Next talk, Nathan. Okay, shall we start?
This equation is correct.
Yep. Yep. So, Nathan, please.
It should be whatever. Okay, okay, I'll start again. I apologize. Okay, sorry. Okay, so sorry, I will continue. I'll start again because I was muted. So we have this mean field. So far we've only spoken about the single, the non-instructing electronic picture, where we basically threw away all of the electronic terms in the Hamiltonian, so we could solve this. We use a single electron separable idea, where we can solve the total molecular wave function in its single electron pieces. And what we do is we use this mean field. To take the theory further, we want to introduce the electronic interaction. So the true electronic Hamiltonian is it's not. The electronic interactions are kind of unsolvable in this single electron picture, but what you can do is you can add in this mean field term. Now, I quite like this figure because it kind of shows you what the mean field is actually doing, and it kind of makes a lot of intuitive sense. So we had the electron density peaks around the nuclei, right? So we saw that in the previous plots, and this is kind of the three space picture. So kind of the mean electron density is always going to be greater around the nuclei because they're attracted due to the Coulombic interactions. So you got this. Can we treat this background fixed potential with our Hamiltonian? So the idea is quite simple. Can we get this extra mean field term? And the mean field, formally the mean field is defined as kind of the density. So you integrate the density. Yeah. So you basically, yeah, this basically gives you a three-dimensional plot of these electronic nuclear cusps. So, so now we've got this. So now we have this term, which is essentially if you notice, we've integrated out all the variables here. So this is just once we have the density, it's just the constant. So let's assume we have the density for now. Then we can solve this mean field Hamiltonian with the separable methods that we had before. So what we can use to solve the global molecular wave function, we can use a product of singular electronic wave functions, and this is known as the famous Hartree product. Again, this was determined in about 1929, I think, by Hartree. He was an expert in differential equations from World War I in ballistics. So then he was at Cambridge and then basically applied all that knowledge to solving differential equations of the Schrodinger equation. Yeah. So there's a product of single electron wave functions. And because the mean field operator is still a one electron operator because we've integrated overall space out the distance, we can use this. But it's not antisymmetric, and electrons are indistinguishable. So there's a lot wrong with it, but I'm just trying to show you the motivation. So it turns out that although when you have the density, it is solvable. So say if we're given some electrons in space and the spin orbital, we can solve this here because this term can be solved, and then this is the potential term, and this is the kinetic term. But you might notice that when you solve this, you get a new solution of the spin orbitals. So this is it's a nonlinear equation. So you get this by solving this input density, you get a new density here. And for one set of spin orbitals, you solve the equation, and you get a new set of spin orbitals. So it's this nonlinear equation. So what you have to do is you have to keep iterating over this. And this is called, you might have heard of what's called the cell-consistent field, because the field has to become, this field term has to become consistent and become, kind of optimized to kind of this constant. Now, I must say, we can't use linear combination of atomic orbitals in this approach because but I should say, sorry, there are some, the reason why there's no basis here so far, this is all just using differential equations. So this is an integral differential equation. And they are solvable in some cases. So the famous one is, again, the spherically symmetric nuclei. So you can actually solve the Hartree-Fock equations, or the Hartree equations, for a nuclei. So you can, for example, fluorine with lots of inner core electrons, you can still solve that exactly because of the spherical symmetry. There's some quite nice. If you look online, there's some very good some great resources showing this. But as soon as you go away from spherical symmetry into molecular picture, then you kind of have to start solving things with a basis. So you need to use a basis in the same way that we use linear combination of atomic orbitals. But due to numerical problems, those aren't suitable. Okay, so, and I will come on to why that is in a second. But as I said before, this is a very crude picture, I apologize. But when you go to helium, so this is the first solution. This is the first case of the Schrodinger equation where you have core electrons, 2 electrons. You start noticing that you get these antisymmetric and symmetric solutions, whereas in reality they were only observing these antisymmetric solutions. So this was kind of the first case where they started to think, it was like experiment, this kind of first proof that that antisymmetry is needed. Okay, so what is antisymmetry? So it's quite simple. Because the electrons, the physical solutions were antisymmetric, they realized the electrons had to be antisymmetric with respect to particle exchange. I just put because the universe. Apparently, if you go to quantum field theory, there is actually derivations for this, but it's kind of observation for our purposes. So going into the previous method where we have this Hartree product, we take this single electron picture, but we give it the constraints that it has to be antisymmetric with respect to particle exchange. So we take the simple 2-electron Hartree product, 2 spin orbital Hartree product, and we see that obviously that because there's 2 terms, we have this normalization factor here, 1 over root 2. And we show that we've moved, that should be, sorry, yeah, there's a mistake here. These x, that should be 2. So these x's should be swapped. But basically, you see you have this swapped over term, which is the exchange. And that very neatly can be expressed as a determinant. So if you take the determinant of this, you'll then get this, and you get the equation from the previous slide. And then we represent it kind of compactly as this ket. So the ket contains the antisymmetry here. Now this generalizes to n electrons, or n spin orbitals, with, so n electrons, and it has all the same properties. So if you know with determinants, if you move columns and rows, you'll flip the signs, things like that. Okay, so what this is showing is that we have this single electron picture, wave function, this product wave function, but it can actually account for the antisymmetry. Okay, so you can see here, as you exchange the columns, you get the sign flipping. And exchanging the columns is equivalent to exchanging the electrons. Have this bracket notation. Okay, so what does this do to our operator? So I don't have time to derive the Hartree-Fock equations, but you just have to take it from me. If you go back to this equation, so this is the mean field equation. So we have this mean field term where we're integrating over all the spin orbitals, all their positions. Now, in the presence of antisymmetry, you basically get this result. This falls out, and your mean field term has what's called the Coulomb term, which is kind of electronuclear. So the electronic interactions got a physical understanding, and then you've got the exchange term. Now, this doesn't have a physical interpretation. It's purely a facet of the necessary antisymmetry in the equation. But you can see the difference is there's still 2 electron. We're still integrating over the 2 electron over the density here, but then on the exchange, to get the density, but here you've exchanged these 2 particles. So it looks like a 2-particle operator, but you're actually integrating out the variable, so it's still a mean field operator. So it's a bit confusing. And because this is a 1-electron operator, is it integrating out the terms? So I think it's quite remarkable, really, that you have a 1-electron operator that still accounts for antisymmetry. Antisymmetry is a property of 2 particles. But, so yeah, so this is a solution for the whole whole molecule. And we've got the sum over I here, where I is the number of spin orbitals. And then J is the number of spin orbitals as well. Yeah. So you've got the Coulomb term, which is an average instantaneous point charge repulsions, which is that the density. And then the exchange term, which exists only to antisymmetry. And this causes a lot of problems. So one of the exercises will be to kind of try to understand this a bit more. So we can then take the Hartree-Fock molecular operator, and then we can, because it's a one electron operator, we can then use the same trick of using separable differential equations, and we can solve a single electron picture. And this gives us what's known as the Fock operator. This is really important. So what is the Fock operator? So we have inside the Fock operator, we have our kinetic term, and then we have our term which accounts for the, and the potential is contained in here as well. Yeah, so we have, so we call this a one electron operator. And we take the, so this has got the one electron kinetic and the one electron potential. And then we have the mean field potential term. The mean field potential term, which contains, which kind of is our approach in this picture to have electron-electron interactions, which has this exchange, this Coulomb term, and then this exchange term where we've flipped over where we've exchanged there. So it's quite strange because you're solving. You have the J's you run over all J's, and then I is the solution that you're trying to solve for. So that's what you get here. So it's so again you have this kind of feedback loop where you're solving for I, then I's got to go back into the equation. Okay. But again, we have this iterative self-consistency condition, but now we've got this kind of anti-symmetrized mean field operator. So you can think of Hartree-Fock as just an anti-symmetrized mean field operator. But it must be solved iteratively, and that's why you might hear self-consistency used. Okay, so this was all solved, for the purpose of the previous discussion, we were just treating this as a differential equation, as if it could be solved analytically. But we know that it can't for molecules. So for multinuclear centers, there's no analytical closed form solution. So we have to solve what's called the Fock, these are called the Ruthian equations. And essentially, it's the secular equation, but with it's the secular equation with the Fock operator. And it's a nonlinear equation because we have this feedback loop. So we introduce what's known as a finite basis. Now, as I said before, we can't use the linear combination of atomic orbitals due to numerical problems with orthogonality. But we can still use the ideas from the generalized secular equation. But the problem is we need to find a basis. So what is a basis? And this is something which is very subtle, and I think is where a lot of people kind of get confused in quantum chemistry. So you have, essentially we have this spin orbital, and we introduce, so let's say that this car analogy is quite nice. So the black here is the exact wave function, right? But we want to introduce a basis So we have these weightings, these red circles are these eters, and we can weight the eters with this C. And the more eters that you have, the better approximation to your overall wave function will be. So the basis is kind of like you mangle it together to the shape of the orbitals that we showed in the hydrogen picture. So it's quite subtle. Like you have this molecular bonding picture, but it's made up of these smaller blocks, which is like your Lego, essentially. So it's really quite subtle. So the stuff we show for benzene, things like that, you essentially build that from a smaller set of basis functions, we call them. So if you've got more balls, a larger basis, you'll get a more accurate answer. If you have different shaped balls, so typically you have different angular momentum shapes as well, you get a better fit to exact wave functions. So there's a huge amount of research in quantum chemistry into building basis functions for different things. So, for example, you might have SCO3G, 631G, double zeta basis sets, things like that. Okay, so typically what you do is, rather than balls, they're formal mathematical functions where we're trying to fit the exact wave function onto, with these with this finite basis here. Okay, so typically, like a good example is Gaussians. So you combine a load of Gaussians. So how it works is that in the 70s and the 80s, people spent a long time fitting these basis functions to get the mathematical functions, these eters. So the Gaussian parameters, like the tweaking, these were done quite rigorously by like Popel and his colleagues at the Popel basis sets. So now, essentially, we just have this fixed set of Lego blocks that we apply to our problem. So we can then build these fitted build our density structures, for example, for our bonding orbitals from a set of Gaussians, for example, or Slater-type orbitals. And what's nice, because of what I said about the variational principle, the Schroeder equation will always find the minimum energy for a finite basis. So you can obtain your bonding orbitals by directly just solving the Fock Schroeder equation. So it's very powerful and very cool. And this is why we haven't got to quantum computing yet. This is why you need to do all this like old school quantum chemistry first to build the shape of the molecular orbitals, because you have these numerical parameters which are your basis functions, numerically fitted basis functions, which then build up these orbital shapes like benzene and hydrogen, etc. H2. Okay, so the basic examples of the basis functions, the two main ones are, for molecules at least, you have Slater-type orbitals, which are exponentiated to the single power of r. We know from the Kato theorem, which is basically says that the nuclear cusps are like these finite peaks. This is exactly what these Slater-type orbitals, these Slater functions, fit, right? And the problem is they're very mathematical. They require a lot more mathematical work to solve them when you start applying them into the Schroeder equation. So typically, just for numerical purposes, we use Gaussian-type orbitals, because the reason for this is the product of two Gaussians is Gaussian. So you can then iterate that over these four-center Gaussians, and then you get a single Gaussian. So it makes the numerical stuff much easier. So you can see here in this figure, so this is the Slater-type orbital, and then we've got these Gaussians best approximating it. Yeah. So we have lots of Gaussians. Linear combination of Gaussians, you can quite accurately fit these Slater-type functions. So what Popel and colleagues did was they basically fitted loads of Gaussians to these Slater functions. So STO3G is Slater-type orbital, but it's made of Gaussians. Okay. It's Slater-type orbital free Gaussian. Okay. So let's take this. If we now, this is where it gets quite advanced. So we take the spin orbitals that we had before for this. This is the Fock equation, the Fock operator. So for the energy, we're integrating. So this is a bra operator ket, but we're just not showing it in Dirac notation. We're integrating over all space for a single spin orbital. Now we expand out the we expand out the operator in terms of the spin orbitals. We're going to get the one electron exchange in the Coulomb term. Now, when we apply this equation, the basis equation, so say we picked some basis functions, eta. We then substitute that into the previous equation, and the Fock operator takes this form. Okay, so you notice now we've got this extra. So the g's are these orbital integrals, and then the c's are the weightings of each of these basis function terms. Okay, so the Fock operator just got a lot more complicated, and you can see that because we have, if we go back, because we have orbitals inside the operator, when the Fock operator then has these C parameters inside of it. So you can see, like, yeah. So really importantly, the Fock operator has orbital parameters inside of it in the basis expansion. Now you can see, you can now see why that would be nonlinear, because you solve F, which has C in it, to get C. So you still have to start looping around. Now, and so going back to our benzene example, so we're not using atomic orbitals now, we're using this arbitrary basis expansion. Okay, let's say STO3G. Now, by solving the Fock operator, the Ruthian equations, each eigenvector solution is one of the spin orbitals. Okay, so you can see here, say if we had some rough p orbital-like basis functions, but made of Gaussians, then the linear combination of those all add up to be like the delocalized p here. So these are all mathematical objects now. And you can see we end up with the same result. And again, because this is the sector equation, which comes from the Rayleigh-Ritz variational principle, this is the minimum energy for each spin orbital. Okay. So just to clarify, so inside the Fock operator, we have these basis function overlaps. Now these are just Gaussians here, these etas. So you're just doing 4-center Gaussian overlaps here. So there's quite a lot of hardcore numerics going on here. Okay. So, summarize. So Hartree-Fock is essentially, it's an anti-symmetrized mean field approach. And it's used as, it gets the rough electronic structure correct. So it's kind of, Hartree-Fock really does explain a lot of the chemistry quite well. So like you can see here, by solving the Ruthian equations, so I did this with Gaussian a long time ago. But it gets the chemistry correct. Like this is what you see in molecules. The qualitative picture is correct for Hartree-Fock most of the time. The problem is when you want that 1% of energy to get the transition state correct, that's when you need higher order structures. But Hartree-Fock is responsible for all of the kind of chemical properties you see in higher order methods, if that makes sense. Like the orbital structures, the orbital shapes, they all come from the Hartree-Fock calculation that you do. So that's why it's so important to verify. And like most importantly, these C eigenvectors are the shape of the spin orbitals. So you need to do a Hartree-Fock calculation before a higher order quantum computing calculation to get the shape of the spin orbitals, which contain the spatially dependent interactions in the second quantized formalism. Yeah. So it's passed on to the second. Yeah. So what I mean by the fact that Hartree-Fock is passed on to the second quantized full configuration interaction, coupled cluster, or quantum computing calculations is that now we're coming back to the quantum computation Hamiltonian that I showed you at the beginning of this lecture. Now you might understand the significance of why you have to really respect Hartree-Fock to get the interaction parameters. So you can see here, so this is your second quantized chemistry Hamiltonian. Now, these I and J's, these are the spin orbitals, which are themselves linear combinations of basis functions. Okay. Now, the I and J's, so obviously when you multiply out the I and J's in their basis expansions, you get all the linear combinations coefficients come out. So the Hij terms are these like rank 4 tensors. Sorry, the rank 2 tensor, and the Gij-KL is a rank 4 tensor of these Gaussian integrals. So this double thing is exchange in the Coulomb term. But you can see that you have these you might do your quantum computing calculation and you'll get a chemistry Hamiltonian. The terms contain all the information about the shapes of the orbitals, basically. That's the moral of the story. So your interaction parameters in second quantization contain the Hartree-Fock molecular orbitals, expansion coefficients. So that's why you need to do this lower level of theory calculation first and then apply. And I'll explain why you need to do a higher order theory in a second. So Hartree-Fock, almost perfect. It typically gets at bonding at equilibrium geometry 99% of the energy is correct. But at bond breaking and bond forming lengths, it breaks down. I'll show you why. And most importantly, strong electron interactions, like strong correlation, is not treated well by Hartree-Fock. So more accurate methods on quantum computers are needed. So here's an example. Okay, so I've got 2 minutes. Here's an example of where Hartree-Fock starts to break down. Okay, so you've got your 2 hydrogen atoms at equilibrium geometry. And then you can see here, as you stretch your 2 hydrogens, Hartree-Fock starts to get way beyond the exact. So you have, and so there's this other method called configuration interaction. So the exact here is the infinite basis limit. So very interesting. But the CI is the same basis as Hartree-Fock, but it seems to get the dissociation limits correct. So what is configuration interaction? So if we go back to our nice, so this is now not, we're not thinking about the linear combination atomic orbitals, we're thinking about Hartree-Fock, but the solutions of the spin orbitals are the same as you saw before in the benzene example. But if we have if we think about the ground state, the single determinate wave function, the ground state of hydrogen, the H2, we have it's 2 spin orbitals, so we have 1 sigma G solution times by another sigma G solution. So the sigma G solution, the ground state, as we showed before, has this. So we're kind of we're just showing that it's got this s orbital-like character. It's a positive interaction of two s orbitals. Now, if we just roughly multiply the two things together, we get this product, which this is just quadratic equation. But what you see when you multiply this out is you get 4 cross terms, okay? Now, the 4 cross terms actually end up being what we have here is both electrons on one, both electrons shared, both electrons shared, both electrons on the other one. Okay. Right? Now, if we think about when we want to go to the really dissociated bonds, you don't want all the electrons want to be on individual atoms here. They don't want to be isolated on one. Okay. So you can see you get these really unphysical allowed solutions in this expansion. So the electrons, at long distances, the electrons really want to be separate, basically. So so you can see you've got these terms here which shouldn't really be there in the long separation limit. So this single determinant picture is not adequate. So that's why we have to use this method called CI. And CI is really what motivates us to use quantum. It's the same problem that we use for quantum computing as well. And that you start to introduce these extra expansions. What do I mean by that? So extra determinants. So you have this many electron multi-determinant wave function now. So what you do is you take the solutions of the Hartree-Fock. So you've got all these different Hartree. So each one of these lines here, 1, 2, 3, 4, these are solutions to the Fock matrix. So these are eigenvectors of the Fock matrix. But I've just put them here as, so you can see, so we've got sigma bonding G, and here we've got sigma bonding G multiplied by sigma star U, antibonding, sigma star U, and then sigma G, antibonding, so bonding, antibonding, bonding, and we've got 2 antibondings. So we introduce these extra determinants. So this kind of seems a bit arbitrary, why we're doing this. But if you look now, when you combine the totally bonding and anti-bonding ones in a linear combination, now this is very important now. So we've gone from the single electron picture to the many electron basis. So this is now a wave function of 2 electrons. Okay, so we're out of the single electron picture now. So this is what. So by having this many electron wave function, the linear combination of these two determinants, you've got determinant 1, determinant 2, determinant 1, determinant 2, but they're different. And we've got the weighting parameters. What happens is when you work through the maths, basically the dissociated terms, you can basically, the C's, you get basically the C's cancel basically here. So you have the C's, these are equally contributed, but then it causes the long expansion terms, the separable terms to cancel. You end up with the truly physical solution, which is the separated, only the separated S orbital. So you've got SASB, SASB. And so if you were to solve the Schroeder equation for this picture in the main electron wave function, you'll just get this, basically. This is one solution. But you can think about it in an intuitive way. So yeah. So this is what you get. So now the bonding is described correctly at long distances. because we only have these separated terms. And you get the physical terms. So this is really the motivation for configuration traction. So configuration traction is a complete generalization of this problem. So now we've left Hartree-Fock behind, okay? Hartree-Fock gives us each one of these black lines. It gives us the spin orbital shapes. And then we have this many determinant wave function, which this here is a 6-electron wave function. And then we introduce all possible combinations of excited determinants. Okay, so as you saw before in the H2 example, we only added an extra determinant. But in the general case, you just do all combinations of all possible excitations. So you got here we have this is called the reference wave function, which is the ground state. It's the lowest occupations of the Hartree-Fock solutions. And then here we have the single excitation, the set of I should say this is a set. So this is all possible singles. So this is just showing one single, but this represents all possible singles. So we can have. So A is the hole, and then R is the particle. So you get this particle hole excitation here. And then we have the same for the doubles, where we do all possible double excitations. And then the full solution goes to the all possible excitations here. And this is it's equivalent to exact diagonalization. You might have heard of that in physics. But in chemists call it configuration traction. Because if you think about it, you're introducing all these extra configurations, electronic configurations. And then the wave function is essentially this. So you have the C0 reference coefficient. This is just the Hartree-Fock energy, by the way. Hartree-Fock wave function. This is a solution of this is the product of all the single electron Hartree-Fock solutions. And then we have basically all the weightings for singles and all the weightings for the doubles, sum neighbor, occupied virtual, etc. So we often call this the occupied space and then the virtual space. Okay. Now we get our old friend the Schroeder equation. Because we have a basis and a Hamiltonian, we can apply the Schroeder equation, and we still get this optimal, like the solutions of this will be optimal for the ground and excited states. But now this is, whereas before the basis scaled with the size of the basis set that you choose, those Gaussian functions, here you have a combinatorially scaling matrix, okay? That's really bad, okay? So a lot of kind of quantum chemistry for the past 40 years has been devoted to solving this equation efficiently. It's just a generalized eigenvalue problem. And essentially, so this is scaling with, well, I mean, if you were just to naively solve this by diagonalization, you can only really do up to like 10 spin orbitals. The largest known numerical solution to this uses iterative diagonalization methods, which is essentially, it's called a Krylov method, and it's basically allows you to, rather than solving the matrix exactly, you approximately solve it using matrix vector products and iterations of that. The largest solution of that with the Lanczos method is 44 spin orbitals, 22 spin orbitals, 22 electrons and 44 spin orbitals. So you can't really do any large molecules interestingly with this, and you're not going to get over, like the amount of effort that they put in to get one extra spin orbital there was crazy, because you're fighting against a combinatorial scaling problem. So this really motivates the need for quantum computing, because if your basis scales combinatorially, it's actually slightly less than 2 to the n, the combinatorial, in this case, as a particle number. But you can really see why we need quantum computing methods, because quantum chemistry has been stuck here for about 40 years trying to solve this problem. Okay, we're not going to get past it with like classical methods, really. I mean, it's just a hack. All the new methods are hacks to solve this slightly more efficiently. Like, how can we keep the most of the wave function that treats the interesting part of the wave function? But if we really want to solve this problem fully, we need quantum computers to go to like interesting systems. Now, there's lots of arguments in quantum chemistry that we don't need to treat the whole system. We only need to treat the sites of interest, like the active sites, things like that. Garnet-Chan will probably tell you about all his methods in perturbation theory, solving the chromium dimer, and DMET, for example. So the argument is true that, is it necessary to solve this for everything? No. But for some systems which have very strong electron correlation, this is needed. So, and the nitrogenase example that does the whole process in the soil is a good example of this. And very importantly, this gives you excited states as well. So you get the excited state, because this is the matrix eigenvalue problem. Okay. I'm going to briefly talk about this. So what is second quantization? I mean, I briefly alluded to it, just because probably people are familiar with it. The second quantization essentially takes the distance dependence from the wave function, so you don't have any of these functions of R anymore for your wave function. It takes that and then puts it into the operator, as you saw in the previous slide. Then it means that we can treat the basis in the occupation number formalism with just ones and zeros. And it gives us this rigorous mathematical footing. This is what, one Neumann-Ising. And basically the determinant-like properties that we saw in first quantization, where you can exchange the rows and columns, etc. These are all represented in the same way by these fermionic creation and annihilation operators. So you see, you have this vacuum state, which is this empty ket. Then you excite this, and you get a spin orbital p existing. Same way it happens here. You can destroy chi p. You get an empty ket, and you can just apply them in succession. And then you can see this is the really important one here. So you can see if you destroy p, if you apply them in this order, yeah, PQ. If you exchange PQ via the use of the fermionic, rather than exchanging the rows of the theta determinant, if you just do it via the fermionic creation annihilation operators, you still get the same properties. But this is now done rather than at the wave function level by moving around the determinants. It's done at the operator level via these operators. Okay. And there's obviously all these famous commutation relations here. Anti-commutation relations, I should say. Sorry. Whoops. Yeah. But the main idea is that these operators preserve the symmetry. Okay, so finally, I guess, this is kind of, so what we've just spoken about with configuration interaction is known as post-Hartree-Fock. But as I said, these post-Hartree-Fock methods require Hartree-Fock to be done beforehand. So that's why you need to download PySCF before you do your quantum computing calculation. You run your Hartree-Fock calculation, you give it your nuclear coordinates, you choose your basis set, you then get an output of optimized orbitals and electronic integrals. You then give these electronic integrals to your configuration interaction, or you could use couple cluster, or whatever method, there's more of them. But in particular, the point here is that quantum computing just is exactly the same as configuration abstraction, basically, in terms of what it requires to be run beforehand. So you need these optimized integrals in the second quantized formulas for quantum computing to work. I'll probably stop there, I think. Yeah. Okay. Cool. Any questions?
Thanks, Nathan. Question? No question.
No?
Okay, let's take a break. Next, Nathan talk will start to, yeah, I think that's, yeah. Yeah, next Nathan talk will start at 20 past 11. Please take a seat. Okay. Okay, let's start the final talk of morning session. Yeah, next one, please.
Okay. I'm going to start because I realize I've spent 2 hours talking about classical quantum chemistry rather than quantum computing quantum chemistry. So we're going to start talking about that now. Someone asked me a very good question in the break where they were like, where do the qubits come into the configuration interaction? So basically, the qubits can like represent occupation numbers by, if you look at these configurations here, this would be, this would be a 12 qubit problem, and you'd have a qubit in, the first 6 qubits would be 0, 1, 1, 1, 1, 1, and then the final 6 qubits would be in 0, 0, 0. So you can see all the possible combinations of 1s and 0s which come from the 2 to the n possible qubit configuration. You get from, the qubits can represent all the configurations this way. So it's actually interesting because the configuration interaction only stays within 6 particles, but the qubits can obviously have all zeros as well. So the configuration scales less severely for a given particle number than the whole qubit space. Okay. And then the matrix elements of this operator are just the typical second quantized ones that you've seen before. Like this guy. Okay, so let's start talking about some quantum computing stuff. So we can typically because the matrix scales it combinatorially, we have to truncate it for real problems. And if you notice, we can actually form our basis using the second quantized representation. So if you see, we can form the excitations by starting from the Hartree-Fock state, which is the 1, 1, 1, 0, 0, 0 state. We can then form an excited thing on that by destroying one of the virtuals and creating one of the excited orbitals with a CA-I, where A is the occupied and I is the virtual. So this is called this is an excitation operator. So we're generating the basis here, and we call these T's the excitation operators here. So we got our single as excitation and our double as excitation. Okay. So this truncation means that you might hear it's called CISD, singles and doubles. This is precisely because that we wanted to have all possible excitations. That would be a gigantic matrix which we can't fit on our computer. So we truncate it to the single and double level to make it manageable. Now, this is where, and then couple cluster, talk about it very briefly, basically takes this linear operator and exponentiates it. And by doing that, you get basically more of the wave function back for the same cost, because you get the cross terms from the excitations coming from the expansion, the exponential expansion of the operator. So basically, couple cluster gives you more bang for your buck when compared to the same T operator. Now, couple cluster motivated the first quantum ansatz for quantum computing, and this is a unitary couple cluster. And basically, you take this T, which is non-unitary, and then you basically exponentiate the T minus the complex conjugate. And this is now a unitary couple cluster object. But the problem is, when you try and solve this with classical quantum chemistry methods, this is non-terminating. But you do a nice trick in quantum chemistry. So yeah, here's what the things look like. So we have Ti is it's called the cluster expansion coefficient. And then the unitary form is just this. Now, to get it to work on a quantum computer, we do this trick called trotterization, which basically takes the exponentiated unitary operator and we expand it to some degree rho, typically row 1 is fine, so we just take the first order trotter. And then we get this, basically. So basically what this is doing is you break up each excitation in the expansion into its own exponentiated unitary operator, and then you apply them in series as a product. Now this has a form that can be implemented directly on a quantum computer. So psi naught, remember, is our Hartree-Fock wave function. This is the initialization state, if you want, reference state. This is the 1, 1, 1, 1, 0, 0, 0, 0, 0, etc. in the lowest occupied state. We then act on that with our unitary operator, these products of exponentials, and then we have our unitary couple cluster ansatz. Now, how do we get this onto a quantum computer? Oh. Yeah, and one thing, the ordering can be important here. And it can give a better ansatz. So there was some work by Gon at Chan showing that you can actually get the exact wave function if you get the ordering correct. All right, so how do we get this onto a computer? Here's a nice iron trap. I'm not biased, but they are the best. So what we have to do is these Tij, these Tn's, these are our fermionic creation annihilation operators. Now, you may have heard of something called the Jordan-Wigner transform. We need to map these fermionic creation annihilation operators to our to the Pauli operators, which can then be implemented directly on a quantum computer. So you might have seen this before. So this is the Jordan-Wigner mapping. We have a fermionic excitation operator, and then this is essentially we have a product of the product of z's. The z's keep track of the antisymmetry. So if you're acting on orbital 4, we have z acting on 0, 1, 2, 3. And then the actual flip operation is done by this x minus y here. And then that is equivalent to fermionic creation annihilation operators this way. And this is the same for so this is the creation minus x minus y, annihilation x plus iy, sorry. So applying this to our excitation operators, we get some quite gnarly things. So this is, but you can see here, you can see you can see where the x minus y's and x plus y's come in. Sorry. Because we have two creation annihilation operators. But basically, you have the z strings, then you have like this quadratic pair, and then you have the z for the doubles. You have the z strings, and then you have these quartic set of 8. So you get 8. So here you got the Jordan-Wigner transform for the fermionic excitations. Here, you go from 2 sets of fermionic creation annihilation operators, and then you end up with 8 for the doubles, and then 2. And then 2 here. So the doubles scale much worse in this picture. And there's lots of ways you can generate these things. So this open fermionic history we have in Quanto. But so we have to exponentiate these. Now we have these. We've done the Jordan-Wigner transform. We have to exponentiate these Paulis. So there's a really famous way to do this, which is if you take one thing away from this lecture, this should be it, because the Pauli gadget is the most powerful primitive in quantum computing, in my opinion. It shows up everywhere. Once you spot it, it's really easy to make algorithms with. So we've got this exponential set of Paulis from our fermionic Jordan-Wigner transform. We then, it might not be that obvious to you, but this is a multi-qubit RZ rotation. So you can I encourage you to, in the break, maybe turn this into a Z, so with no rotation, and then come in with a 1, 1, 1, 1 state, and then work through it, and you'll see that it works as a multi-qubit parity operation. If you then were to add a rotation in a Z basis here, you then get this really powerful e to the I theta over 2 Z, Z, Z. So now you've got an exponentiated, parameterized parity rotation. Now this is really powerful for many things, including Hamiltonian simulation, like these unitary couple cluster ansatzes. And then we can change that now to n, so that was just a Z, Z, Z. Now we can change that by just a basis rotation on each side of our C0 ladder. And then we get any parity gadget we want. So this is really powerful. So now you can get an exponentiated parity word. And then what the coding exercise this afternoon is going to be basically building a Hamiltonian simulation from this structure. Okay, so this is really like, it's very powerful because now you can have access to Hamiltonians and cluster operators exponentiators. Okay. Okay, so now let's talk about VQE. So VQE in quantum chemistry is probably, because as you saw the quantum chemistry Hamiltonian has n to the 4 terms, it's a fully interacting fermionic problem. It's probably not, VQE is probably not going to be very applicable to quantum chemistry in my opinion. But it's still going to be useful for state preparation and things like that, so it's worth learning about. So VQE is essentially this. So you have the state preparation. The state preparation is this ansatz that I showed you before. This is your wave function. And you want to have some parameters so you can change your wave function. You then have then you have to measure that Hamiltonian. And you can do that by individual parity terms. I'll explain that in a second. Then you have to measure, so you apply the Hamiltonian, then you measure it. Okay, and then you repeat for each Hamiltonian term. Okay, so U can be anything. It can be unitary couple cluster, it can be hard efficient, it can be whatever ansatz you want. It just depends on how expressive it's going to be, if you will get there to represent, how accurately you'll be able to represent the ground states. But we're not, so far this isn't even a VQE. This is just for one set of parameters, I want to measure a Hamiltonian for P. Okay, so we haven't changed it. VQE is the process of updating the parameters. This is just a single energy calculation. So if we look at the first point, these are quite old slides, so I'm used with Qiskit stuff. But if you see here, this is the unit, you can see in the slides, so you can see these C0 ladders, right? These are each of the excitation operators that we showed, these fermionic creation annihilation operators. So you've got this set of fermionic operators. You've got a set of exponentiated fermionic operators. Sorry, set of exponentiated Paulis, these Pauli gadgets. So you've got these chains of Pauli gadgets, and you've got a parameter at each one at the bottom of these C0 ladders. That's a unitary couple cluster ansatz. So by changing these parameters here, you can change the energy, basically. People like the unitary couple cluster ansatz because it's got some physical representation. Because you actually have, it's representing the excitations of the operator from the Hartree Fock state, so you can actually get a picture on what the orbitals are doing. Whereas if you're just using hardware efficient ansatz or some random mess of entanglement and rotations, it's very unphysical. Okay. It's kind of like tensor network methods and CI in classical space. Whereas tensor networks, you lose the kind of orbital information. It's just a mangled mess of nonlinear parameters. Okay. So we've prepared our state with our ansatz. We want to now take our operator. How do we measure our operator this is in NISQ setting? So you can apply the same Jordan-Wiener transform our states was prepared by fermionic operators, exponentiators, but the operator is also containing these fermionic operators. So we have to Jordan-Wigner that into something which we can apply on a quantum computer. So the weighting coefficients here, when you apply the Jordan-Wigner transform, some program will probably spit this out for you, but you can, if you do it by hand, you end up with something like this. And there's some mixing happens between these, but for H2, you end up with 15 terms. And you have to measure it, and then the weightings are these parameters, weighting each Pauli string, they're like related, they're not the same. And then the Paulis are related to the fermionic operators. They're not the same, that's just showing what they correspond to. And it's similar to measuring the density matrix elements. So basically now, in order to calculate the total energy of the system, you have to prepare your state, and you have to measure the red, which are these Pauli strings, which are applied to these qubits. And then you have to times it by its weight, the interaction coefficient, and then you loop over all the terms in the Hamiltonian. In the chemistry setting, these are the classically computed integrals, but if it's the Fermi Hubbard, these are just parameters. But what I'm trying to say is that the only quantum part in this calculation is the Paulis. The coefficient is just outside. This is done with post-processing. So how do we measure the density matrix elements? Well, they're kind of the Pauli version of the density matrix elements. So this is quite subtle. It's known as a technique of operator averaging. So you might be like in your quantum computing algorithm, click measure, calculate excitation value. But what's actually happening? So if you're measuring in so if you have a Pauli ZZZ, for example, if you measure it in the z-axis, basically you had 3 qubits. If you had 0, 0, 1, you have a parity of 1. 0, 0, 0, you have a parity of 0, etc. Now the parity of these basis axes measurements, which corresponds to if it's a Pauli Z, Pauli X, Pauli Y, from the previous equation, the parity of the shot measurement on the outcome corresponds to the eigenvalue of the Pauli. Now, by measuring over many times, you'll get a mixture between 1 and parities of 1 and 0 in the shot outcomes. That'll give you a mixture of eigenvalues between 1 and -1. You average that over the number of shots, and then you times that by the weighting coefficient, and that will give you the contribution to the energy of that Pauli term. Okay. So yeah. This is quite a subtle thing. So and then the VQE. So this figure is from the classic paper by Romero and Ryan Babish, Jared McLean. So what this is showing is it's like VQE basically. The Rayleigh variational principle saves you again. So you can basically just twist the parameters in your state preparation, and if it goes down, you're saved because you have a convex optimization problem. Basically, what this is showing is you prepare your state, you measure your state and get the energy from the method I just showed, and then you calculate the energy, and then you change the parameters just so that the energy will go down, basically. So you have a gradient optimizer or whatever optimizer you use. But basically, you're changing the parameters such that the total energy of the system goes down. And the key point here is that you have this measurement of Paulis at each step, and you're summing over each term in the Hamiltonian. Okay. So yeah, you just change the parameters in your ansatz until your energy gets to a minimum. But obviously, because your ansatz is, there's a large amount of choice in the ansatz, right? So your ansatz might not be good enough to get one ansatz might be able to get, for the same operator, one ansatz might be able to get to lower energy than another ansatz. Or on the other case, you might have this barren plateau problem or local minima. One ansatz might get stuck in a local minima from a different initial set of parameters, which is bad. So the reason why I say that, and this is, in my opinion, I don't want to say it's not going to work or be useful, but like for calculating energies, it's certainly not the exact right use case for it, because the amount of measurements you need, we know quantum computers, we have a finite budget of measurement cost. These variational algorithms require a huge amount of measurements. Like you're looping every term in the Hamiltonian, and then you're changing the parameters each time. So there's lots of reviews now with the same VQE. It will take like hundreds of years to do anything useful for chemistry. So that brings me to quantum Krylov methods, which I think are a useful application of quantum computing for NISQ stuff. So we go back to exact diagonalization, where we're building. Remember, we have this huge basis. I'm going to speak now about quantum Krylov methods, which is probably, I would say, is the nearest term application of NISQ for chemistry, I would say. And it kind of leverages the classical quantum balance in a slightly different way, which I'll explain. Rather than with VQE, where you're leveraging the classical cost on the gradient optimizer and the quantum cost on the shot measurement, and the sort of energy measurement for the operator averaging. Here, you do something slightly different, which I'll explain. So going back to exact diagonalization or configuration interaction in chemist speak, we have this exponentially scaling basis. This matrix obviously scales exponentially. This is, it's combinatorial, but it's within 2 to the n. Well, yeah. I'll explain that if I want to explain that. Go ahead. So we have this exponentially scaling matrix. This is bad. Okay. So what Krylov methods do is it's a very general method. It's really cool. So you again start with this Hartree-Fock method, but then rather than expanding your basis via excitations, you expand your basis via powers of functions of the Hamiltonian, a number of k times. So if you see, and typically the dimension of k is much smaller than the dimension of the previous matrix. So you'll scale, these are typically in the order of 100, maybe less. Whereas like before you're you're scaling exponentially. And the basis obviously scales just like this. So you have your wave function is now a linear combination of your reference state plus your first state, which is the first power of the Hamiltonian function, etc. Okay. And then you still have this generalized eigenvalue problem, but it's much smaller. Okay. Now, obviously, the complexity is being hidden inside this function of h. Okay. But we'll talk about that now. Wait a second. So, and then if you think about the Krylov generalized eigenvalue problem, the matrix elements are these things. So hij is now, you have this reference, bracket reference, and then you have the function of h to the I going to the left, function of h to the j going to the right, and then you end up with this matrix problem. So the ij matrix elements are formed by, the ij basis functions are formed by f to the h to the I and f to the h to the j. And the overlap matrix elements are formed in exactly the same way, whereas now there's no h, so we just have this function of h to the I, a function of h to the j. So clearly, this is different. Even though the basis is smaller, the eigenvalue problem we need to solve is smaller. These elements are much more complex. So we can't just solve these via operator averaging or whatever. Like these functions require a bit more thought how to implement them. So there's a number of different ways to do them. There's a kind of three famous ones. So you have real-time evolution. So So this is the function of h to the j that you apply is the time evolution operator. So powers of the time evolution operator are just n times t in time. Okay? So you've got f to the h to the j, as a power of the time evolution operator is just e to the iht jt. Okay. Right. And the reason time evolution seems to be very popular because there's many proposals to do time evolution efficiently on quantum computers, albeit in a more fault-tolerant setting. But you can see that there are ways to do time evolution quite cheaply if you just have small t and low j's. It's obviously more expensive than VQE, but it's definitely cheaper than phase estimation. So it's, yeah. And then if anyone's confused about what the function of a matrix is, the function of a matrix is defined as a singular value decomposition where the function acts on the singular values. Because if you think about it, SVD is just a rotation, a scaling, and a rotation. So you can just scale, you can just act on the scaling part, and then the rotation will be fine on each side. And another famous function of H in Krylov method is imaginary time evolution, which is kind of, so you're just basically missing the I here. So this will propagate all the states. You'll get this linear combination of basis states in the original space, in the eigenvector space of this. And then imaginary time evolution, if you're not familiar with it, so I've done a lot of work in both these areas. But imaginary time evolution is essentially it's a way to propagate to the ground state. It's a quantum way of doing optimization. So if you propagate an imaginary time evolution far enough, you'll only end up with the ground state. So it's a non-unitary evolution because if you think about your initial state being a linear combination of all possible eigenvectors, the ground state is just one eigenvector. So you're killing all the other eigenvectors apart from one. So it's not a rotation, like a unit rotation, it's a projection. So this is difficult to implement on a quantum computer, but you can do it, and I put a paper out yesterday on it. And then finally, this is kind of the very sexy topic at the moment in quantum computing is the Chebyshev polynomials. And these are kind of, the way I think about them are, the double angle formula that you learn about at A-level or whatever high school diploma you did. And then if you recursively do that to n to the power n times, you get the Chebyshev polynomials, basically. And these have recently been shown can be implemented by Grover's reflections recursively, iteratively. So I know Callum may have given you a tutorial on that. And then finding these functions is really open. Implementing these functions on quantum computers is a really open research area. So this is quite a hot topic at the moment. Okay, so then you can take this further and make the whole thing unitary. You can even change the eigenvalue problem itself to be unitary. So you can take real-time evolution and then take the Hamiltonian operator and make that itself a unitary rather than it being the Hamiltonian operator. So you're now solving a unitary generalized eigenvalue problem rather than the original one. And the eigenvalues are related so that the phi n's here are the solutions of, so the lambda n's are related to the solutions of e to the iht by this, and then are related to the eigenvalues of the original Hamiltonian by this equation. So what you can do is you treat your, so we're working in the time evolution space. We're using time evolution as a function, a Krylov function. But then we also do the operator as the Krylov, so we replace what was the h. So what was before was this h. We've now replaced that with e to the, we now replace that with e to the IH2. So what you can do, which is really cool, is because these are all exponential, you can just add together all the powers. So you end up with this much smaller and simpler object here, right? So this is really powerful here. And you just reduce the complexity of your problem massively. Because if you think about it, you only have to calculate, like the overlap and the Hamiltonian Matrix elements can be calculated from the same set of objects, right? So you end up like reducing I think you go from a quadratic to a linear scaling problem this way. So this is really cool. And then this can be implemented, so this is what I'm trying to say here. So the overlap and the unitary Hamiltonian, whatever you want to call it, elements are from the same set. And they're generated from this smaller set here of K. And these are just transition matrix elements, right? So this is your reference state acting on a time evolution operator, turning it into another state, and then taking the overlap. Now, these can be implemented very easily on quantum computers, and cheaply-ish, if you think medium-term cheaply, with the Hadamard test, where the Hadamard test, we're taking that time evolution operator, controlling it, and then doing the Hadamard test with that. And then doing that for different values of K, you can generate this object. So we need, this is a complex value here. So we need, this is a complex value, so we need the real and imaginary parts of this. So that's quite easy to do. So you basically, to get the real and imaginary parts of the Hadamard test expectation, you do basically the Hadamard test, but then you have an S here. Now, you can generate the energy of this is calculated from E0 minus E1 here. So you basically calculate a difference. But like this object is quite straightforward to calculate. That you can there's a nice I can show you the proof of this, but showing that this is an expectation value is quite straightforward. You just have to combine the shots in the correct way. You have to do some post-processing on the shots, but it's straightforward. I think it's E1 minus E2, end shots. Someone correct me. Okay, so now you can see, so what I mean by this is leveraging the quantum classical balance in a different way, is that the quantum balance is now thrown into, you have to do this small set of Hadamard tests, where you have to do this controlled time evolution operator. So there's a lot of complexity hidden inside this box. So like trotterization is the simplest way. I will speak about that later in the fourth lecture. But there's a whole field like looking at different ways to improve time evolution operators. So time evolution is really a subroutine for many algorithms. So learning how to do time evolution is crucial, I think, if you want to work in quantum computing. Okay, yeah, and so the balance, so the classical balance is really this matrix problem that you're offloading everything to. But that's quite small now. And the quantum balance lies more heavily than BQE, but in these time evolution, controlled time evolution operators. So I've also got a paper implementing this as well, if people are interested. It's under the name of variational phase estimation with variational fast forwarding, where we basically try to do some approximate compilation of these objects to solve the same problem. Okay, so we've got 15 minutes to talk about phase estimation. That is not enough time, but whatever. Okay, so we have. Okay, so now we're moving on from the kind of hybrid methods where there's a balance between the classical part and the quantum part. We're now moving into the fully quantum algorithms. And the famous one of these is called quantum phase estimation. Okay, so many of you may have read this. Nielsen Chuang is really good. And we can use this in quantum chemistry to a great advantage. So what is quantum phase estimation? So whenever we have a unitary acting on an eigenstate of that unitary, the phase will be generated into, the phase will be generated from the operation. So we get, and it's the eigenphase, we call it. Now, we can apply that to, like, we can use that property in quantum chemistry. Look, there should be a minus here, sorry. We can then use this phase idea. So if we have an eigenstate of the Hamiltonian and we apply e to the IHT to it, we then get this object, which is like a phase, but the phase contains EJ times T. Okay, so the idea of phase estimation is essentially, can we exploit this and get this out, basically? So can we implement this and get this e to the I out? And again, this is going back to what I said before in how phase estimation for quantum chemistry uses time evolution as its main primitive. So there's a lot of papers in phase estimation that study the complexity of phase estimation for energy values, where you change the method of Hamiltonian simulation that you use. So a lot of the Google papers, they like to use computational and use Chebyshev polynomial frameworks, and trotterization, etc. LCU. Yeah, I will speak about all of these next session. Okay, so can we get the eigenvalue? So what's actually happening when we think about phase estimation? I like this. So as a physics person, or well, quantum chemist, I should say, I like to think about physical problems rather than kind of a computer science approach to things. So if you look at what if we do have an eigenstate of the system, and we apply this transition matrix element, and you measure, so this is measured along the, this is time along here, and this is the real and imaginary part. You get this perfect spiral where the phase just propagates you in time, like this. And it's quite nice. And it's essentially the phase is related to basically the distance between these spirals, which is really cool. Now, if you don't have an eigenstate and you have some linear combination of eigenstates, which is what we have in practice most of the time, because if we could form the ground state, then we'd solve the problem. So, and this is one of the things that has caused a lot of issues with phase estimation, whether it's useful or not for quantum chemistry. But you can see here, the mass, if we have a linear combination of eigenstates, we then basically get weightings of the competing phases in here for the different eigenstates. And that results in kind of this messy spiral where you've got all these different phases coming out. And you have the weightings of each eigenstate. Oh, it's here. But this is how I think about phase estimation. It's a really nice physical way of doing it. Okay, so the canonical form of phase estimation, the old school way that you'll see from Nielsen and Chuang, is basically, you have to really understand the motivation for it. You have to understand the quantum Fourier expansion. So I'll do my best to explain this. So obviously we know the Fourier expansion basically says that any function can be expressed as an infinite weighted sum of cosines and sines. And you can see this here. But obviously in computers, we don't have an infinite matrix. We have a finite dimensional matrix and finite dimensional vectors. So we have to truncate this to some realistic amount. And this is essentially what happens. So you get an approximation here. Now this underpins most of modern signal processing. And there's lots of people that say that the fast Fourier transform is the most powerful algorithm invented in the past 100 years, etc. But that you can take this sine cosine sum. I'm going quite quick, but you take this sine cosine sum and you can always form an exponential of that. And then basically what that means is that your Fourier expansion can be represented as a sum of exponentials, where the exponentials have the specific power relation. Okay, so it's quite a... So you can see, you take a vector y can be formed by acting with these omega nk's to the n, and these omega nk's are these complex exponentials where you have the index n and k up here divided by n. Okay, and it is basically magic that you can trust this, but it does work. And then I think about it, I'm much easier thinking about these things in a matrix form. So you can think about the quantum Fourier transform as this linear map or a basis transformation. So you're just basically rotating the input basis into this new basis where the first one nothing happens to it. The second one is times by omega. The first element's either 1, second time, and it times by omega, omega squared, and etc. Then you get these powers going down here. So this one goes up to the power of 1, the power of 2, the power of 3, etc. Okay. Now, you can think about this. The way that I think about these problems is basically a matrix vector product, where this linear map is a unitary matrix. And we know that unitaries can be implemented on quantum computers. So the game of the quantum Fourier transform is to implement the discrete Fourier transform unitary on a quantum computer. Okay. Now you can see if we take a simple 3-qubit example, so the classical discrete Fourier transform, that would be an 8-dimensional or 8-dimensional discrete Fourier transform. You can see here the first line is the power of 1 to the x. Yes. And the second line is x to the power of 2. What you see is here, when you get to x to the power of 8, you loop back around because you get this is one of the things that you have this equation here. That you always loop back around in the Fourier transform. You end up with these 1 states. And this is a 3-qubit. I say this is a 3-qubit. We aim to implement this as a 3-qubit thing because we've got a 2 to the power of 3 by 2 to the power of 3 unitary matrix. Okay, so now to really understand the quantum Fourier transform, you have to understand binary notation and sums of how you can get the integer values from the binary values. This is something I struggled a lot with, so because computer scientists are quite native with this kind of stuff, but I was certainly not. So if you think about, in typical binary notation, we have the x here represents the value in the binary, and then you have the 2 to the k is k is the position, and then 2 to the k is the value of the bit. Okay. So this is position 2, bit value 4, position 1, bit value 2, position, you see what I mean, 2, yeah. Ooh. So we can then, basically, we can get the integer value by just summing our x's and our 2 to the k's. So this is 6, it's 4 times 1, 2 times 1, 1 times 0. Okay. Now, quantum Fourier transform uses fixed point binary fraction notation. So this is the same idea, but we shift the decimal point, and we do it with fractions. So here, it's a bit confusing, but we now use the position is 1, 2, 3, 4 to the right of the decimal point. And then we do, rather than times in by powers of 2, times by powers of minus 2. Sorry, minus powers, 2 to the minus powers for the position. So you can see here, this is, the bit value is 1/2, a quarter, 1/8, or 16th. And then we times it by its bit value. So you can see 1 times 1/2 is 1/2, 1 times a quarter is a quarter, plus 1, and then 1/8 times 0 is 0, and 1/16 times 1 is 1/16. And we add these together, and then this basically gives us our fraction, binary fraction, which represents our decimal. So the more bits you have, the higher resolution you get. And we represent it, whenever there's a square brackets in my notes, this is a binary fraction, so just be really careful with that. And this really did confuse me a lot. So maybe I'll leave this for a second because it's really central to the quantum Fourier transform. Okay, so this is quite heavy, so you can try and follow the derivation or just get the main idea. The main idea that you map between two states. But what that mapping is done by is, what the mapping is given by these equations. So remember we had that, so we have a 3-cubic example. So we have this ij times k over n. Now this is n in the 3-cubic case is 2 to the power of 3. So these exponential powers that we have here, in the 3-cubic case, which is 8-dimensional, so n equals 8. I realize I've changed the indexing, so I apologize, but you can see it's basically over n here, instead of but we put it in a cubic form, so it's 2 to the power of 3. Okay. And then we've normalized it with cubic form as well, so it's 2 to the power of 3. Or kind of, I say cubic form, I mean just the powers of 2. Okay. Now, this is a fraction, and we can explain that using the binary fractions that fixed point binary fractions that I showed before. Now, 1/8, 2 over 8, 3 over 8, etc. Then take this binary fraction form over this KL, which is either 1 or 0. And then we can represent this integer as a bit string. And you can see now we've got this sum of an exponential for each KL. So it's quite natural to break this exponential up into its constituent tensor products. That's what we do now. Okay, I'll send you these slides. Don't worry about trying to understand it. But the main idea is that you basically break up the tensor product. You use the binary fraction notation to get sum of this weight of this coefficient. You then use that to break it into tensor products for each bit. And then use this very powerful idea that nice idea that when you have k to the 0, you have exponential of 0, which is always 1. So then you get basically all the terms on the 0 vanish, and you just get these terms on the 1. And this is a product state in quantum information. So there's actually been a lot of work suggesting or proving that the quantum Fourier transform is classically simulatable, which is well known, but it doesn't generate strongly entangled states. Okay. Yeah. So what you can do now is you can then, for all these binary fractions that you have for the j's, you can basically take out the whole number, and there'll always be a dominant fraction. So you have half, a quarter. The halves can be represented as the simplest binary fraction, fixed point binary fraction. The quarters can be represented as a 4-element term, and the eighths can represent it like this, etc. I encourage you to work through this. Okay. So then you end up with this binary fraction kind of mapping. You get x to this e to the binary fraction. Oh, yeah, and you can. I'm rushing through this, but you can when you expand the binary fraction, which is a sum, into its exponential terms, you can see where the quantum Fourier transform comes from, because you have h. This is just two. This is a h, and this is e to the power 2, and 3 here. And you can kind of see it acting on each qubit this way. Again, I encourage you to work through this. But basically, you basically can map from one state. You basically map from the non-Fourier coefficients into the Fourier coefficient states. You've got your bit string state, and it goes to this Fourier basis state. And then the quite subtle step in Nielsen and Schwang is this kind of mapping from it. You map back from the integer bit. You map back from the integer mapping to the bit mapping to the integer mapping, which is very. This is very confusing. Okay, but basically, and the generalization is this, and you can see you get more and more higher resolution fractions. But the game of the real light bulb moment happens when if you think that if you have an input state for a given phi in this form, because this is the Fourier basis, the quantum Fourier transform will map from that to the bit string. So you can read out the binary fraction of the phase from the input Fourier basis. The problem is getting the system into the Fourier basis to read out the phase. Now that's the game of quantum phase estimation, is how do we get the phase into the structure which can be read out by the quantum Fourier transform. So that's what phase kickback is really. So you may have heard this properly called phase kickback. So when we have an eigenstate, when we have an eigenstate, when we have a controlled unitary acting on an eigenstate, you can see that the unitary is applied just to the 1 here. This is a controlled 1U. But then, because this is the eigenstate, the phase just gets generated, and we can just form this product. So it's almost like this wasn't even touched. We just have the phase gets kicked back onto the ancilla. So this is how we get the input state of the quantum Fourier transform in the way we want. This is the game we play to get the right input state of the quantum Fourier transform to read out the phase from the Fourier basis to the phase basis. Okay, and then we can, as we noticed, there was powers of phases in the input state of the inverse quantum Fourier transform, I should say. Sorry. So we just did that by applying a powers of u to the m. So you can now see. Let's have a look at this example. So you can see we apply the Hadamard to the first one, and then we apply these powers of controlled unitaries, and then we end up with these powers of controlled phases. And remember, this is an eigenstate here. Ooh. Now we've got this we've got this Fourier basis here. We want to map out the Fourier basis to get this phase. So we read out the phase from that, and then the phase can then be extracted via this binary fraction equation here. Okay, so how do we then apply that to eigenvalues? So the idea is the same. But rather than our controlled unitary now is our controlled time evolution operator. And the phase that we're trying to calculate is Ej times t. Okay. And we're trying to extract this in the same way with the inverse quantum Fourier transform, y successive powers of controlled time evolution operators. This is again an example of where time evolution is so important and why Quantization and using these parallel gadgets is really useful. So again, we have this example. And then we apply these successive powers of this controlled time evolution. We then get this phase. Sorry, there's a phase missing there. There's a t missing there. And then we can extract it this way. And we can then, because the phase is e to the t, and then we can extract the energy from that. Okay, so the problem with the canonical phase estimation is that it's very expensive. So you saw that you had these controlled time evolution operators. These time evolution operators themselves are really expensive things. And there's lots of work to try and reduce the cost of that. And the main one is that you need, so you don't need the eigen, obviously to define the algorithm you need the eigenstate, but you don't need it as long as you have a significant overlap, I think over half. because obviously successive applications of the algorithm will then boost the signal of the correct phase, which is, yeah. Yeah, so as I said, controlled time evolution is really important, and there's lots of different ways of doing it, and I'll explain this. And one of the other problems is obviously you need lots of ancillary, and you probably, I mean, you almost definitely will need fault-tolerant compilation and error correction for these algorithms to work. Okay, I'm going to stop there because I think we've had enough.
Any question?
So as you mentioned, and as it was mentioned the other day, VQE doesn't have any useful applications for near-term, like Nix-error computers, right? Quantum computers. So what are the exact points where like Krylov methods, like at which points do Krylov methods or like these quantum phase estimations, like due to like space or time complexity, or like at which points are they more advantageous? And
for the near term, quantum Krylov methods are the best, I think. But again, it's how you compile these functions of H. I think the simplest trotterized time evolution operator combined with Krylov is a simple way to go. It's probably the best near-term circuit primitive that will be the most useful. So controlled Hadamard test with trotterized time evolution operator. I don't know if that answers your question.
The second part, like at which points does quantum phase estimation, like which of the parts does it show advantage, or like it, like as you mentioned, QPE has practical applications, right?
Yeah.
Like which part of the like the problem encoding makes it so? Like what enables it so?
I mean, there's lots of studies in complexity theory of like the precision needed for phase estimation and things. It's quite hard to compare them to Krylov methods because they're not the same. I would say if you have enough ancillars, phase estimation will win every time because you can get really precise energy values. But I think I think Krylov methods are probably slightly better. I mean, but phase estimation is a long way off, I think.
Okay.
Yeah. That's not a very good answer, I apologize.
So I had another question as well. So Garnet-Chan works on tensor network states for for classical simulations, right, of quantum chemistry. So is there a quantum equivalent of like answers, like tensor network answers, and do they work well, or is it?
Yeah, great question. So there's two ways to approach this. The first one is that all quantum circuits are tensor networks. So you've got a tensor network ansatz if you've got a quantum circuit. Okay, so that's one way to think about it. But there has been this work with my colleagues, Michael Fitzfog, etc., Reza, people like that, where they're doing these quantum tensor networks, which is a slightly different approach where I'm sure you're aware, if you know about tensor networks in like matrix product states, mirror, the bond dimension is a limiting factor, because basically the dimension of the matrix multiplication between the tensors needs to be truncated to a point that it will fit on a classical computer. That sometimes has been shown to scale exponentially for certain problems. So the quantum tensor networks are a way of dealing with the size of the bond dimension on the quantum computer. So if you read the work with my colleagues, I think that's very recent actually. They use the quantum mirror approach. So that's a way of leveraging the exponential scaling of qubits combined with the classical tensor networks, which is a new method. Yeah.
So much.
Thank you very much for the wonderful lecture. I'm not sure if this is like some basic knowledge, but is there a way of getting the ansatz, like a smart kind of method, or is it just like a heuristic method, like a trial and error approach?
So there have been some papers which show in the exponential limit, you can get an ansatz which will get the exact ground state. For example, there's a famous paper, the symmetry preserving ansatz, but I think you need exponential parameters for that to be sure. I personally think that the internal group symmetries give a lot of argument as to why you can reduce the parameters, but that's not really the answer. But with the internal symmetries of the wave function often mean that parts of it don't need to talk because they're in different irreducible representations. That's often represented in matrix problems by like block diagonalization, where you have lots of zeros. So I think maybe it's an ansatz using total spin, for example, to take advantage of that. I don't know if you're familiar with the genealogical coupling of spin eigenfunctions, but you can basically couple spin eigenfunctions in like a tree network. I always thought it would be cool to map a quantum circuit ansatz to that. But then if you want to just go through the heuristic route, you can do this variational compilation approach, which is where you kind of successfully add gates. There's like, there's the adapt ansatz, and there's also, I got to work on this as well, but you basically make the cost function the overlap with some state that you want, and you keep adding gates until you get closer to this cost function, but that's very heuristic. So making ansatzes is a very difficult problem. It's the same thing in tense networks in the classical space. Like, you're just throwing MPSs and mirror problems which don't necessarily have that inherent structure.
Okay, thank you.
Thank you for the talk. I wanted to ask first a technical question about the Hadamard test, where there was a W operation that just wanted to ask which operation is it?
That's a phase gate. So that will give you the imaginary part of the expectation wave. Yeah.
Okay.
So,
And
this guy. Yeah.
okay, perfect. Yeah. All right. And also in the same slide there is that the wave function scales linearly with a qubit number. I was wondering if this means an advantage respect to the classical numerical methods, or
yeah. So this this is probably badly worded, but what I'm trying to say is that the basis dimension here is, so you can represent an exponential number of states in this part by a linear number of qubits, because you have 2 to the n possible, like 1 to 0 combinations. Whereas you have to store this explicitly as a vector in a classical space. So you've got to store an exponentially scaling vector. So you have a linear object to store rather than an exponentially scaling object. But there's a lot of other problems with storing the quantum state. It's not as simple as this one-to-one comparison.
okay. And last question about phase estimation. If there was any, like, since with phase estimation we get a bit representation that is an approximation of the real eigenvalue, I was wondering if it was possible to apply any rescaling to the operator that we are applying in order to get integer eigenvalues and so more precise bit representation of the eigenvalue.
So you change the time step, sort of, in the phase almost. Wait, no. That's a very good idea. I'm not sure easy that would be able to apply to the canonical form, because that algorithm is kind of like a recipe that you can't really touch. But I actually have some slides on some modern approaches to phase estimation that I will talk about in the next slide, which kind of do use a similar argument. You use different time step lengths, which can still calculate the phase. But it's not quite a rescaling, but it's just a different way to get the phase. But yeah, I hope.
Okay, thank you so much.
Yeah.
Another question?
Can we go back to the phase gadget?
Yeah.
The palette gadget?
Yeah.
Yeah, okay.
My favorite primitive. This guy.
Yeah. So you suggested that people put in a bunch of like cats and analyze what happens.
Yeah.
Shouldn't the students instead use the powerful and convenient stabilizer formalism to analyze what happens with these circuits?
I like to think about everything in terms of states, because I like wave functions flying around.
Masochism.
Yeah.
I think if anyone's interested around the break, I'll show people how to decompose this circuit with the stabilizer formalism and show that this, executes some Pauli gadget.
Okay, let's thank Nathan again. So, afternoon session will be given at the labo at the Adriatico Guest House from 2 p.m. Yeah. So, yeah, lunchtime.